We've confirmed over 5,000 exoplanets, gas giants, hot Jupiters, ice worlds orbiting dim red stars. But in all of that catalog, not one Earth-like world has ever been seen directly. Its atmosphere measured, its surface hinted at, not yet. NASA is building a telescope specifically designed to change that. And the key piece of technology, a tiny optical mask, smaller than your hand, that manipulates light in a way that seems almost like physics trickery. The mission is called the Habitable Worlds Observatory, the first space telescope whose primary goal is to detect and characterize potentially Earth-like worlds orbiting sun-like stars. Its target, nearby stellar systems. Its ambition, a census of life-friendly worlds. Most exoplanets were found by watching stars dim when a planet crosses in front of them, the transit method. Powerful, but limited. Earth-like worlds in Earth-like orbits rarely transit. And even when they do, you can't study an atmosphere in detail through a shadow. You need to see the planet directly. But direct imaging has one devastating problem. Astronomers describe it like this. Imagine you're trying to spot a firefly sitting right next to a blazing lighthouse while standing miles away. That's more or less what detecting an Earth-like planet next to its star actually looks like from Earth. In numbers, an Earth analog is about 1/10 billionth as bright as its host star. Not 1/10, not 1/1,000,000th, 1/10 billionth. The star doesn't just outshine the planet, it buries it under a mountain of photons. You might think, just build a bigger, sharper telescope. But the problem isn't just brightness, it's optics. Even a perfect mirror smears out the image of a star due to two unavoidable effects: scattering from microscopic surface irregularities and something more fundamental, diffraction. When light waves squeeze through the circular aperture of a telescope, they bend and spread. That's diffraction. A star never arrives as a perfect point. Instead, it blooms into an Airy pattern, a bright central disk ringed by concentric halos of light, spreading outward like ripples in a pond. And those rings are bright enough that any planet orbiting near them is completely swamped. You're not looking at dark sky next to a star. You're staring into a luminous halo, and the Earth-like planet is hiding somewhere underneath it.
The fix is a century-old device called a coronagraph. Invented in 1930, it was designed to block the sun's blinding disk so astronomers could see its faint outer corona, normally hidden in daytime glare. Block the bright source, reveal what surrounds it. Simple in concept. For exoplanets, extraordinarily hard in practice. At the heart of a modern stellar coronagraph sits the optical vortex phase mask. Unlike a simple opaque disk, this mask doesn't block the starlight, it twists it. It imprints a spiraling phase pattern onto the incoming light, rotating continuously around the mask's center, like the helical thread of a screw.
This is called a helical phase delay. When coherent, on-axis starlight passes through the spiraling mask, different parts of the wavefront are shifted by different amounts. The waves no longer reinforce each other, they cancel. This is destructive interference, and it works precisely because the star sits exactly on the optical axis. Instead of converging cleanly at the center of the focal plane, the interfering wavefronts scatter outward, pushed into a ring far from the center. The starlight is still in the system. It hasn't disappeared. It's just been moved to the wrong address. At that outer ring sits a physical aperture called a Lyot stop. It simply intercepts the displaced starlight and absorbs it. What remains at the center of the detector is mostly just off-axis light, including the signal from the faint nearby planet. Because the planet is offset from the star's optical axis, its light enters the mask at a slight angle. The helical phase patterns affects it differently. It doesn't trigger the same destructive interference. The planet's photons travel through, converge at the focal point, and reach the detector largely intact. Fabricating a mask that achieves this precisely across a wide range of wavelengths is one of the hardest problems in modern optics. At NASA's Jet Propulsion Laboratory, researchers have found a promising path forward using thin, flat layers of liquid crystal polymers, or LCP. By precisely patterning the polymer's molecular chains in a spiral arrangement, the JPL team can dial in the exact phase response needed across a broad color band. In laboratory tests, these masks have already achieved 1 in a billion starlight rejection, an extraordinary engineering milestone. But 1 in a billion isn't enough. The Habitable Worlds Observatory needs 10 in a billion. To close that gap, researchers are exploring metamaterials, nanostructured surfaces made of arrays of microscopic posts, each tuned in height, width, and shape to produce optical properties that simply don't exist in nature. Each nano-post is individually customized. Together, they form a mask capable of the precise achromatic phase control needed to hit that 10 billion to 1 target. If it works, and the physics says it should, the Habitable Worlds Observatory will do something no telescope has ever done: image an Earth-like planet directly and read the chemistry of its atmosphere for the very first time. We've been watching the stars for thousands of years. We've built instruments of staggering precision, and now, with a mask barely larger than a coin, we might be about to answer the oldest question in science. If that's the kind of story that keeps you up at night, subscribe, and I'll see you in the next one.